processor and applications. The main objective of this presentation is identify the most important DSP processor architecture features and how they relate to DSP applications. Then what is DSP, digital signal processor? A specialized microprocessor for real-time DSP applications. We have three types of models are there. First one, digital filtering. Second one, fast Fourier transform. Third one, convolution, matrix multiplication, and etc. In digital filtering, we have finite impulse response and infinite impulse response. In most of the DSP, we have three blocks are available. First one, analog digital converter. Second one, digital signal processor. Third one, digital to analog converter. In ADC is nothing but analog digital converter. It's got input from analog, input in the form of analog. It will produce digital output signal. This output digital signal is going to DSP. Then in DSP block, the signal is processing in the form of digital and it will be produced to the digital output. Then again DAC is nothing but digital to analog converter. It produces the analog output waveform. Hardware used in digital signal processor. We have four types of hardware are used. First one, ASIC. Second one, FPGA. Third one, GPP. Fourth one, digital signal processor. First, we have to analyze the performance. First one, ASIC. The performance is very high, as well as FPGA performance is high. GPP's performance is medium. DSP performance is medium, intermediate to medium to high. The next characteristics, flexibility. ASIC flexibility is very low. FPGA flexibility is high. GPP flexibility is high. DSP flexibility is high. The next characteristics, power consumption. ASIC power consumption is very low. FPGA power consumption is low. GPP power consumption is medium. DSP power consumption is low medium. The next characteristics, development time. ASIC development time is long term. Then FPGA development time is medium. Then GPP development time is short. Then DSP development time is short. The next, the common DSP features. First one, hardware architecture used. Next one, dedicated single cycle multiply accumulate. It's nothing but MAC instruction, hardware MAC units. The next one, single instruction multiple data, SIMD. Very large instruction word, VLIW architecture. The next one, pipeline. Next one, cache. Next one, direct memory access. Why we go for DSP, digital signal processor? First point, digital signal processing algorithms need lot of mathematical operations on every sample of data. They need to be done quickly before next sample of data arrives. Deferred processing is not possible. General purpose processors provide add, subtract and shift operations. They provide multiply and divide, but typically they take a lot of memory cycles. Why DSP is needed? General purpose processors also suffers from space constraint. They also consume lot of power. Hardware features visible through DSP. Hardware modulo addressing. Second one, memory architecture designed for streaming data. They may support several memory accesses per cycle. The next one, direct memory access. Next one, multiple arithmetic units. Next one, Harvard architecture. Features of DSP. Special SIMD instructions are used. Some processors are VLIW, very long instruction word techniques. Specialized instructions of DSP like MAC, multiply and accumulate word work quickly. Special algorithms are packed as libraries for quick functionality. Bit reversed addressing that would help in calculating FFT. Deliberate exclusion of memory management unit. They do not support virtual memory. Data operations. Saturation arithmetic operations that produce overflow will accumulate the maximum number as the result. Fixed point arithmetic, single cycle operations. History of DSP. Originally, bit slice processors are used for implementing DSPs. Example, AMD 2901, it's a 4-bit processors. By connecting several AMD 20. Multiplier and multiplier accumulator. Array multiplication is one of the common operations required in DSP. Example operations that require array multiplications are convolution and correlation. Correlation is two types. First one, autocorrelation, second one, cross correlation. The next, one of the important requirements of array multiplier is that we need to process the signals in real time. Operations related to one sample need to be connected before next sample arrives. If sampling frequency is 100 Hz, the operations needed by the present sample need to be complete before 0.01 seconds. Higher the sampling frequency, lesser the time available for computation based on present sample. How to construct a real-time array multiplier? We have two approaches to construct the real-time multiplier. A dedicated MAC unit may be implemented in hardware, which integrates multiplier and accumulator in a single unit. Example, Motorola DSP 5600 series have separate multiplier and accumulator. Example, for this approach, TI DSP 320C5X series. Here, output of the accumulator is stored into product register and content of product register is added to accumulator register in the central ALU, arithmetic logic unit. In both the approaches, MAC operations can be completed in one cycle. Thus, the presence of hardware multiplier and multiplier accumulator is one of the mandatory requirements of PDSP. P is nothing but programmable DSP. The next, how the array multiplier operates. Here, the input signal, present sample and previous m samples are array x equal to xn, xn minus 1, xn minus 2 up to xn minus m plus 1. And the array input corresponding to the impulse response of the sequence is h, h0, h1, h2 up to hm minus 1. The output of the nth sampling instant yn is obtained by multiplying the xn with the array of h. Xn is nothing but input sample, then h is nothing but impulse response. Then how x of n plus 1 is obtained by shifting xn so that n plus 1 the sample becomes first element and all the elements of X array are shifted right such that ith element of xn becomes I plus 1, the element of x of n plus 1. The content of the product register is added to accumulator before new product is stored. Further, the content of direct memory access is copied to next location whose address is direct memory address plus I. Howard next slide discusses about hardware architecture. In hardware architecture, we have three blocks: physically separate memories and paths for instruction and data. First block is data memory, second one program memory, then third one CPU, central processing unit. This is the basic architecture of Howard. This is the overall microprocessor. We have four blocks. First one data memory, second one instruction memory, third one arithmetic logical unit, then fourth one control unit. In ALU, we are getting from input from analog and it will processed and then it will be access to data input or output anything. Then again ALU got input from control unit, then control unit got from input from instruction memory. Then we have clock section, then control and address bar, then output is got from ALU. Howard architecture. This employed an entirely separate memory system to store instructions and data. CPU fetched the next instruction. It also fetched data simultaneously. Its unique feature is instruction address space and data address space are separate. Each address space can have the same address, so that address does not uniquely specify a memory location. You also need to store which address space you are referring to. This will use two buses, one for accessing instruction and another one for accessing data. Modifying Howard architecture. In a pure Howard architecture, mechanism need to be provided to load programs into program memories and initial data into data memory. Modern machines use multiple buses. One will access both memory, program memory and data memory. One will access only data memory. Data can also be transferred from one memory to another memory. This feature is used in modern day programmable digital signal processors. This is helpful at start time to as constant data can be transferred from program memory to data memory. The next architecture is Von Neumann architecture. In Von Neumann architecture, we have again three blocks. First one control unit, second one arithmetic logical unit, third one memory unit. The next one input and output. Von Neumann architecture explained. It employs one address space. Instructions and data are stored in the same address space. The PC refers to the next instructions. It takes the instruction, examine it, and the instruction would be having pointers to operands. If the pointer get corrupted, there is a possibility of program abandoning as it fetches instruction and then data. This architecture is slow. So programmable digital signal processors rarely use this architecture. Advantages of having multiple buses. Number of access memory cycle can be increased. Motorola DSP 5600X series, DSP 96002 have 3 memory buses and 3 memory access cycle. TMS 320C54 series have 4 memory buses and 4 memory access or cycles. Multiple access memory that permits more than one memory access per cycle is called multiple access memory. Dual access RAM technology permits 2 memory access per clock cycle. 4 memory access are also possible if dual access RAM memory is connected to programmable digital signal processor with 2 independent address and data buses. Single cycle MAC unit. In single cycle MAC unit, we have a flow chart. Multiplier have 2 input signal, one from A, then another one from X. The multiplier output is going to adder. Then adder have 2 inputs. One is A I minus 1, X I minus 1. Then another one is A I X I. Then both the signal will be added in adder blocks. The output is going to register. This is the basic formula for a single cycle MAC unit. Direct memory access DMA. The feature that allow peripherals to access main memory without the intervention of the CPU. Typically, the CPU initiates DMA transfer. DMA is nothing but direct memory access. Does other operations while the transfer is in progress and receives an interrupt from the DMA controller once the operation is complete. Can create cache coherency problems. The data in the cache and may be different from the data in the external memory after direct memory access. Require a DMA controller. Multi-ported memory. Number of accesses can be increased using multi-port memory. Typical 2-port memories will have 2 memory address buses and 2 data buses. Thus, 2 different chips need not be used in Harvard architecture. Disadvantage: increased complexity, more number of pins, more area and increased cost. Cache memory. Separate instruction and data LI caches. This is nothing but in hardware architecture. Most systems used direct memory access. The next one, pipeline. An instruction may have many phases. First one, fetch. Second one, decode. Third one, execute. Then fourth one, write. Throughput will be low if all these executed serially as when one stage is busy, others are idle. All these stages will be operated parallelly in pipelining technique, which will improve throughput. This is the pipeline diagram. We have instruction fetch, instruction decode, operand fetch, instruction execute, write clock. This is the clock cycle. We have clock cycle, then y-axis instructions level. Single instruction multiple data, SIMD, a technique for data level parallelism by employing a number of processing elements working in parallel. SIMD, instruction pool, data pool, PU, programmable unit. This PU is nothing but programmable unit. VLIW architecture. VLIW is nothing but very long instruction word. Transmit is a chip that uses this technique. TMS 320C6 series also uses similar techniques. This reads relatively large group of instructions. They execute them at the same time. For this purpose, they have many arithmetic logical units, many multipliers, many shifters, etc. VLIW is accessed from memory and it specifies the operations and operands for performing on different data points. It simply increases the number of instructions executed per cycle. Performance gain with very long instruction word depends on parallelism achievable with the algorithm. Very long instruction word features. A technique for instruction level parallelism by executing instructions without dependencies is nothing but parallel. Example of a single very long instruction word is nothing but A, B, E, G, X, Y, Z, H. These are the input signal. F, C, D, W. It's an output signal. It's the comparison between CISC processor, RISC processor, and VLIW processor. We have compared 6 type of characteristics. First one, instruction size, then instruction format, then instruction semantics, register, memory references, hardware design focuses, then picture of 5 typical instructions. First, in CISC processor, instruction sizes varies. In RISC processor, instruction size is 1, usually 32 bits. In VLIW, instruction size is 1. In CISC processor, instruction format, field placement varies. In RISC processor, regular, consistent placement of fields. VLIW instruction format is regular, consistent placement of fields. In CISC, instruction semantics varies from simple to complex, possibly many dependent operations per instruction. In RISC, almost always one simple operation. In VLIW, many simple independent operations. The next characteristics, register characters. In CISC, register is few, sometimes special. In RISC register, many general purpose. In VLIW register, many general purpose registers. In CISC processor, memory references bundled with operations in many different types of instructions. In RISC processor, memory references is not bundled operations, that is load or store architecture. In VLIW, memory references not bundled with operations, that is load store architecture. The next, hardware design. In CISC processor, exploit microcoded implementation. In RISC processor, hardware design focuses explored implementations with one pipeline and no microcode. In VLIW, hardware design focus exploit implementations with multiple pipelines, no microcode and no complex dispatch logic. The last row is picture of 5 typical instructions. The basic, next slide, the basic difference between digital signal processor versus microcontroller. In DSP, used hardware architecture, VLIW or SIMD. In DSP, no bit level operations. In DSP, hardware max. In DSP, we used lot of digital applications. In microcontroller, mostly used in von Neumann architecture. In microcontroller, single execution unit. In microcontroller, flexible bit level operations. In microcontroller, no hardware max. In microcontroller, controlled applications. This is the basic architecture of TMS320C6713 starter kit block diagram. This is the basic block diagram. We have voltage regulator, power plug, USB plug, then DSP. We have used 6713 DSP processor, then CPLD, flash memory, then STRAM memory, then host port interrupt, then memory exceptions, peripheral exception, then LED parts, then DIP, the next AIC23 codec, then micro input, then line in, then line out, then HP out. We have used these types of blocks in TMS320C6713 DSP starter kit. The TMS320C6713i has high performance CPU and rich peripheral set are tailored for multi-channel and audio applications such as broadcast and recording, mixing, home and large venue audio decoders and multi-zone audio distribution. The TMS320C6713 device is based on the high performance, advanced velocity, very long instruction word architecture developed by Texas Instruments. The velocity architecture provides sample performance to decode a variety of existing digital audio formats and the flexibility to add future formats. ATM S320C6713 DSP operating at 225 MHz frequency, 16 megabits of synchronous dynamic RAM, 512 kilobytes of non-volatile flash memory, 256 kilobytes usable in default configuration, 4 user accessible LEDs and DIP switches, software based configuration through register implemented in CPLD. This is the basic architecture of TMS320C6713. So this is the basic architecture. In this basic architecture, we have interfaces STRAM, SPRAM, SRAM, ROM, flash and IO devices. Then we have SPI control port, high speed GTM ports, then AC97 ports, serial EEPROM, then MAC ASP interface to multi-channel ADC, DAC, codec, then multiple outputs. The main 6 TMS320C 6713 features velocity very long instruction word CPU core, fetches 8 32-bit instruction at once, 8 independent functional units, 4 ALU fixed and floating point, 2 ALU fixed point, 2 multipliers fixed and floating point, 32 cross 32 bit integer multiply with 32 or 64 bit result. Load store architecture with 32 bit general purpose register. Instruction set features: hardware support for IEEE single and double precision floating point operations, 8, 16 and 32 bit addressable, 8 bit overflow protection and saturation, bit field extract set clear bit counting normalization. Then 32 bit external memory interface, clueless interface to SDRAM, flash, SP, SRAM, SRAM and EPROM. 512 MB total addressable external memory space, L1 L2 memory architecture, 4K byte L1P program cache direct mapped, 4K byte LI L1D data cache two-way, 256 kilobyte L2 memory total, 64K kilobyte L2 unified cache mapped RAM and 192 kilobyte additional L2 mapped RAM. Enhanced direct memory access controller, 16 independent channels, 16-bit host port interface, 2 integrated circuit bus, multi-master and slave interfaces, 2 multi-channel audio serial ports, 2 multi-channel buffered serial ports, 2 32-bit general purpose timers, dedicated GPIO module with 16 pins, special addressing modes in programmable digital signal processor, short immediate addressing, short direct addressing, memory mapped addressing, indirect addressing, bit reversed addressing, circular addressing, special addressing mode, short immediate addressing. Operand is specified as a short constant. This forms part of the instruction. Length depends on programmable digital signal processor. Example: TMS320C5X series and 8-bit constant could be used. Short direct addressing. The lower order address of operand is specified as part of the instruction. Higher order bits would be stored elsewhere, like a page pointer. Example: TMS320 DSP lower 7 bits are specified in instruction. Motorola DSP 5600X lower 6 bits are specified in instruction. Memory mapped address. CPU register and IO register are accessed as memory locations. This is done by storing them in the initial or final state. Example: TMS320C5X series page 0 corresponds to CPU register and IO registers. Motorola DSP 5600X last page is used. Indirect addressing. Address of operands can be stored in one of the register called indirect address register. When operands are fetched from addresses specified in registers, the registers are updated. This is done having another special CPU or ALU for updating these addresses. Increment can be high or an offset in some special register. Bit reversed addressing. Binary pattern corresponding to a particular decimal number is obtained by writing the natural binary equivalent in reverse order. Therefore, LSB becomes MSB and MSB becomes LSB. Address is incremented or decremented in bit reversed form. Circular addressing mode in real-time data will be continuously coming. If they are stored in linear buffer would be excast. If they are stored in circular buffer, new data would overwrite older data. No need to check whether we have reached the end of buffer. We have linear buffer and circular buffer. This is the linear buffer instruction level. First one xn, then x of n minus 1, then x of n minus 2, then up to x of n minus k. Each input is shifted down by one location. The circular buffer addresses automatically incremented or decremented from first to last location. Example of circular, this is the simple calculation of circular addressing. Limitation of circular buffering. The size of the buffer must be power of 2 power n. The filter length can be any size. However, see example to follow. The buffer must be aligned so that the starting address of the buffer has n LSBs equal to 0. All pointer objects must use the bit reversed update mode. This requires that the desired increment or decrement value be stored in the index register in bit reversed form. Note, all 2 power n data values in the buffer are accessed but not in linear order. This means that all access to the data in the buffer must comprehend the ordering of the data and never modify the circular buffer pointers using normal updates. Methodology for a circular buffer. These are the method for circular buffer. The next, on-chip peripherals. On-chip timer, they generate periodic interrupts to the DSP. They also generate sampling clocks for A to D converts. Serial port. They enable data communication between programmable digital signal processors and peripherals such as analog to digital converter, digital to analog converter, or RS-232 These ports have buffers such that the DSP sends the data and reads the data to these ports in parallel form, but the data is sent out through these ports in serial form and data is read from these ports in serial form. TDM serial porting. A special serial port which permits programmable digital signal processor to communicate with each other devices or other programmable DSPs using time division multiplexing format. Parallel ports. They are faster than serial port. Bit IO port. These are only single bit wide. They can be individually set, reset or read. These bits are used for control purposes or for data purposes also. This is the basic block diagram of TMS320C50. We have data bus, we have programmable ROM, data program SRAM, data program DRAM, data DRAM. We have serial port 1 and 2, TDM serial port, buffered serial port, timer port, host port interface, test emulation, then calculation, CLU, multiplier, accumulator, ACC buffer, shifter, ALU unit, parallel logical unit, programmable controller, program counter, status or control registers, hardware stack, address generation logic, instruction register, memory control, multiprocessing, interrupts, initialization, oscillator or timer. These are the DSP operations formulas. We have finite impulse response algorithm. So y of n is the output, x of n minus k is input signal, ak is a impulse response. So that's why we have y of n is a output signal, finite impulse response filter, y of n equal to, it's a multiplication of input as well as impulse response. This is also same for infinite impulse response, conversion. The next DFT, discrete Fourier transform. Formula is x of k equal to summation n is equal to 0 to n minus 1 x of n e power minus j 2 pi nk divided by capital N. Capital N is nothing but number of samples we have. Then DCT, discrete Fourier transform, f of u equal to summation of x equal to 0 to n minus 1 c of u into f of x cos pi u of 2x plus 1 whole divided by 2n. These are the DSP processors. We have uniprocessor based Harvard architecture, TMS 320 10, TMS 320 C25, TMS 320 C30, TMS 320 C50, TMS 320 C2XXX series. These are the uniprocessor DSP processor. These are the years, then bit size are mentioned, then what's the clock speed, then how many instructions per second, then how many nanoseconds, then device density of the transistors. The next multiprocessor based DSP, TMS 320 C80, TMS 320 C62 series, TMS 310 C67 series. Features of TMS 320C F4X series: high performance low power C54 series, advanced multibus architecture with 3 separate 16-bit data memory buses and 1 program memory bus, 40-bit ALU including a 40-bit parallel shifter and 2 independent 40-bit accumulators, 17-bit parallel multiplier coupled to a 40-bit dedicated adder for non-pipeline single cycle multi-accumulate operations, compare, select and store for the add, compare selection of Viterbi operator, exponent encoder to compute and exponent value of a 40-bit accumulator value in a single cycle, 2 address generators with 8 auxiliary register and 2 auxiliary register arithmetic units, data buses with its bus holder features, extended addressing mode for up 8M 16-bit maximum addressable external program space, single instruction repeat and block repeater operation for program code, block memory move instruction for a better program and data management, instruction with a 30-bit long word operand, instruction 2 or 3 operand reads, arithmetic instruction with a parallel store and parallel load, conditional store instructions, fast return from interrupted. Software on-chip peripherals, software programmable wait state generator and programmable bank switching, PLL clock generator with internal crystal oscillator, full duplex, time division multiplexed, buffered serial port, multi-channel buffered, direct memory access controlled, 8-bit parallel host, enhanced 8-bit parallel host port interface, 16-bit parallel host interface, 16-bit timer with 4-bit prescaler, interprocessor first in first out unit. The 54 DSP uses an advanced modified hardware architecture that maximizes processing power by maintaining one program memory bus and three data memory bus. This processor also provide an arithmetic logic unit that has high degree of parallelism, application specific hardware logic on chip memory and additional on chip peripherals. These DSP families also provide a highly specialized instruction set, which is the basics of operational flexibility of this DSP. Separate program and data spaces allows simultaneously access to program instruction and data. Two read and one write operation can be performed in single cycle. This is the basic internal clock diagram of the TMS 320C54X series. This is in parallel shift register. We have accumulator, CB data bus, DB data bus, PB program bus, parallel shifter, T register, MAC unit, ALU, memory and external interface, peripheral interface, multiplexer, multiplier, fraction, CPU. In CPU, 40-bit ALU, two 40-bit accumulator, a parallel register, shifter, 17x17 multiplier, a compare, select and store unit. In ALU, the perform two's complement arithmetic is 40-bit ALU. ALU can perform Boolean operation. In accumulator, guards bits 32 to 39 bits. A high order word 16 to 31. A low order word 0 to 15. Parallel shifter. The parallel shifter produces a left shift 0 to 31 bits and right shift 0 to 16 bits on the input data. Multiplier or adder. The multiplier adder 17x17 2's complement multiplication is 40-bit accumulation in a single instruction cycle. The multiplier adder block consists of several elements: multiplier, adder, signed, unsigned, input control, fraction control, zero detector, rounder, overflow, and track. The multiplier has two inputs. One input is selected from the track, a data memory operand, or an accumulator. The other is selected from the program memory, the data memory, accumulator as immediate value. These are the compare, select and store unit. The next program unit. The compare and select store unit performs maximum comparison between the accumulator high and lower bits, allows test control, flag bit of status register and transition register to keep their transaction histories, and selects the larger bit in the accumulator to be stored in data memory. Program control is provided by several hardware and software mechanisms. Status register. The status register ST0 and ST1 contain the status of the various conditions and modes of the TMS 320 54X devices. Auxiliary register is AR0 to AR7. These are the 16-bit auxiliary register can be accessed by central arithmetic logic units. The primary function of the auxiliary register is generating 16-bit addresses for data space. Then next, temporary register and transition register. Temporary register is used to hold one of the F2 multiplicants can multiply and accumulate instruction. Transaction register is a 16-bit register is used to hold the transaction decision for the path to new matrix to perform the Vector-P algorithm. The next, stack point register. It contains the address at the top of the system tag. Circular buffer register 16-bit PK is used by the ARU is in circular addressing to specify the data block size. Then block repeat register, interrupt register. The block repeat counter is a 16-bit register used to specify the number of times a block of code is to be repeated when performing a block repeat. Interrupt register, mark register is used to mask off specific interrupts individually at required times. This is the processor mode status register. controls many memory configurations of the 54 series devices. Power down modes. These are three power down modes activated by the idle 1, idle 2, idle 3 instructions. Idle 1 instruction is used to shut down the CPU. Idle 2 is shut down the CPU and on-chip peripherals. Idle 3 instruction is used to shut down the 54X processor completely. Thank you. These are the basic DSP processor and application. Thank you.